Hey everybody, it's Mr. Wolf. We're back with another video for Unit 6. Today we're going to be getting into a little bit deeper into arcs and their relationship to chords and some other things. But we want to start off with a little bit of review, as we generally do, just so you guys are all caught up and remember everything you need to remember from the last video. So we're going to do a little bit of arc review, as it says here. Let's grab a pen. That's what I meant to do. A little bit of arc review. We want to talk about the difference in minor arcs and major arcs. And we also want to discuss central angles. So if you guys remember, arcs are made up of angles. Well, made from angles, I should say. And an arc is just a piece of the circumference of a circle. So we have this point here, which is our center point, and we have these 2 points here, A and B. And we call this angle C. Oh, we don't start with C because that's the vertex, right? Vertex is always in the middle. We start with B or A. We'll call it BCA, and this is our central angle. And there's something we know about the central angle, and we know that the measure of the central angle, no matter what it may be, is always going to be the same as the minor arc measure. So the central angle here, we'll say that looks about 150 degrees. And then from knowing that the central arc is 150 degrees, we can say that arc AB is 150 degrees. And that's our minor arc. But we got to remember, there is a major arc, and we'll express such using the point D. And we can say that, well, there's major arc ADB, and that goes from point A all the way around this way to point D, around to point B. And that measure is going to be 360, since that's the total degrees in a circle, minus our minor arc measure. So ADB would be equal to 360 minus 150, which will get us 210 degrees. So that's just some basic review of arcs. If you're having a hard time remembering some of the other things, I'd advise you to go back and review your notes from the previous video, or go back and maybe rewatch parts of that video. We're going to move on from here. Hopefully you feel comfortable with arcs, because now we're going to talk about arc congruency. Now, when we think of congruency, you think maybe, well, if we had two line segments like AB and another line segment, say DC, and we know that they're both the same measure, just say 4 inches in this case, then because you know these things, you can say that AB, line segment AB, is congruent to the line segment DC. And that's something we learned very early on. Congruency always means same size and same shape. When you're working with angles, it comes down to measure. When it comes down to rays or whatever it may be, it's always the measure. But with arcs, we have a couple different factors at play here. So let's say, and I'm going to draw myself another circle just for the example here. Let's say with, and this won't be perfect, but we'll try. We have this smaller circle here with a center point, and we'll call this center point C, with points A and B out here. And then we have this circle. Let's just call our center point L. We'll call this point M and point N. Just get you guys used to using some different letters here. So we have these two central angles that create arcs. Of course, there's arc AB here and arc MN over here. And let's just say that, well, their central angles both measure the same. Let's say that's, that looks just under 90. We'll just say 80 degrees, just to eyeball it. So we'll say these both measure at 80 degrees. Well, then you'd think, okay, well, we know that the arc measure is equal to the central angle. So this arc, AB, is going to equal 80 degrees. And this arc, MN, is going to equal 80 degrees. So you'd think in this case, well, yeah, they'd be congruent, but that is not the case. There's another factor at play here, and I think if you could probably guess it from looking at it, and that is the size of the circle. So in order for arcs to be congruent, they must have the same measure, and they must be on the same size circle. So I have another circle drawn here. We'll scroll down a little bit. We have another circle here, and we'll say this circle is the same size as the one above it. So in this case, if we had an 80-degree central angle, and we'll call this X, Y, Z, we would know, if we knew for a fact that these are the same size circles, that we could say that arc YZ is congruent to arc MN. So we have that in that case, but there's something else kind of comes into play here. There's more to it than just that. Remember that if a circle has the same measure in arc as far as the degree amount, and it is of the same size, then those two arcs will be congruent. But there is one other little fact here that may just help you even more. We can say two arcs are congruent if their corresponding chords congruent. And you may be thinking, okay, I don't know what this means. And that's okay, because we haven't really discussed what a corresponding chord would be to an arc. But we got to think back about what chords means before we go any farther. Remember, chords are any line that are drawn through the circle from edge to edge. So like that, you could have one here. And remember, the diameter is a chord. The diameter happens to go through the center point. So let's say the center point's here, and you had a chord that went through that. That would be your diameter, and that is also a chord. So what do we mean by corresponding chords to an arc? Let's go on to the next slide. Arcs and chords. So here we have central angle, and we'll label this as I tend to, with A, B, C, C being our center point. And we obviously have this arc AB. Let's think about chords. Chords go from one point on the circle to another point on the circle. So we can say every arc has has a corresponding chord. And that chord will share endpoints with the arc. Let's give a visual example. Let's say, and I'll try to use the line tool here to make it as straight as possible, we had a chord that ran from point A to point B, like that. So we now have chord AB, and we'll denote it like this, like a line segment. So we have chord AB and we have arc AB. And that is an example of a corresponding chord. So let's just give another brief example. I'll draw a circle here. We'll freehand this to make it quicker, but maybe a little bit sloppier. We have our center point, and we have some sort of angle. Let's not make it like that just yet. We have some sort of angle, maybe like this. Then the chord that goes from this point to this point, here, is the corresponding chord to that angle. And what did we say on the last slide? We said that two arcs are congruent if their corresponding chords are congruent. So let's think here. In this case, let's call this XYZ. Let's say we know that this chord is equal to 3, whatever unit of measure you want, but we'll just say 3 for now, and this one's equal to 6. Well, we know that arc AB is not congruent. We'll slash that out. Not congruent to arc YZ because their corresponding chords do not equal. 3 doesn't equal 6. You guys know that much. So let's give an example of somewhere it does happen to work out. So let's say we have something like this. Point comes through here. We have X, Y, and Z. And you take your ruler out and see that you measure this at 3. Then the case is that YZ, arc YZ, is congruent to arc AB. So I may have repeated that a lot, but I'm going to repeat it again. The corresponding arc of a chord shares the endpoints, or the corresponding chord to an arc, I should say, shares the endpoints of that arc. So in this case, we have the central angle from C to C, or ACB, apologies, and that creates this arc AB. And then we have a chord that runs from A to B, and that is the corresponding chord to the arc. Remember from the last slide, two arcs are congruent if their corresponding chords are also congruent. So if you want to determine if two arcs are congruent, look to their chords. You will have examples where you may have to measure these things. You may have and two chords in two different circles, or two arcs on two different circles, and I'll say, hey, are these congruent? And you have to take the ruler, mark the points, draw the line for the chord, or draw the chord itself, and then measure and see if they are congruent. These are things you could run into, so this one's very important. But we'll move on just a tad bit further and talk about inscribed angles. Now you look at this angle here we have drawn here inside this circle. That looks a little bit different than what we're used to. We're normally used to something going through a center point. But now we're talking about something completely new. And these are fun. I love the connections we can make here. So if you know about arcs, these connections should come pretty easy. So an inscribed angle is an angle created two chords share an endpoint. So let me repeat this. An angle created by two chords that share an endpoint is known as an inscribed angle. So we'll say the endpoint's here. We'll call this C. Actually, you know what? To differentiate, we'll go back to the X, Y, Z. Call this X. Call this point Y. And we'll call this point Z. There we go. So we have this, and we have chords here. We have X, Y. And we have chord XZ. And you can look and see that these two chords share an endpoint at X. And that creates angle E, Y, X. So how we have those pieces. We have those pieces, not pizzas. Although this does look like a piece of pizza. And we can create this angle here known as the inscribed angle. Now, here is the fun part. This is a very important fact. I'm going to put important for those of you who are maybe not paying as close of attention. Now's the time because we got an important fact coming up. Inscribed angles, such as the one we have over here, measure half of their intercepted arc. And that's a word we use occasionally, but we haven't used too much. Intercepted arc. Basically, the intercepted arc is just the arc that's created. So in this instance, we're talking about arc Y, Z. That would be our intercepted arc. So, inscribed angles measure half of their intercepted arc. Let's see how that could help us. What if I was to tell you, let me create some space for myself here. What if I was to tell you that arc YZ is equal to, let me think here. What would I want to make that? Let's say 90 degrees. So if arc YZ, this point Y here, to this point Z here, if that arc equals 90 degrees, then what would angle X equal, or angle DXY equal? Let's read the fact again. Inscribed angles measure half of their intercepted arc. So, angle ZXY being our inscribed angle, and knowing that YZ is 90 degrees, half of that would be what we put here. So what's half of 90? 45 degrees. So in this case, we know that our inscribed angle is equal to 45 degrees. Let's review what we just said, because this is brand new material, and this is very important stuff. So an inscribed angle is an angle created by two chords that share an endpoint. You'll see them, they're easy to remember in that they touch all 3 points on the edge of the circle somewhere, whereas the central angles we've been looking at, they have one that's kind of like in the middle on that center point. Inscribed angles are going to be all 3 pieces touching the circle somewhere. And the most important fact about this is that their measure is half of the intercepted arc. If this 90 right here would have been 200, then this 45 would have been 100. If this 90 right here would have been 180, then this 45 right here would have been 90. Very important. So let's go down to a special example here, and something that we may have touched on in the past a little bit, but maybe not enough. So I'll touch up on it a little bit more. We say that an arc of, and I'll separate this wiggly line. An arc of 180 degrees is known as a semicircle. And I think I mentioned this some before. Not how you spell that. But I wanted to make sure that it was mentioned again, because this vocabulary will be thrown around. So an arc of 180 degrees will be known as a semicircle. And here we have an example of an arc of 180 degrees. From this point to that point, all the way around this way, is 180 degrees. And what's that create? Half a circle, also known as a semicircle. So an important fact about semicircles comes when it is intercepted by an inscribed angle. So we have this inscribed angle here. It comes from here down to here, over to here. Now this one looks kind of odd because it's kind of small. The other one up here stretched all the way across that circle. But remember, the biggest identifier, the one I like to use, is that all 3 of those points on the angle are touching somewhere on the circle. So let's say this one over here we'll call this B, we'll call this one C, and we'll call this one A. So A, B, and C points are all touching that circle, so we know it's an inscribed angle. So what are we getting at here? We have an 180 degree arc. Oops, sorry, ignore that. We have a 180 degree arc here, created by AB. And we have this inscribed angle that meets the 180 degree arc, also known as a semicircle, at its endpoints. In this case, it will always equal 90 degrees. So let's see what we just said again. Let's write it down. Any inscribed angle that shares endpoints with a semicircle will measure 90 degrees. And this makes sense, really, because if we look at this, we say that the arc it creates, it's half of that. So we look, what arc comes from this? Well, it's this one over here. So this is 180 degrees. We divide that by 2 to get 90, just as we did up here with all of our examples. Remember, this inscribed angle up here is 45 degrees because the arc across from it, the arc corresponding to it, is 90 degrees. It's half of the arc. Look, we said it again. Half of their Intercepted arc. So what's the intercepted arc down here? 180 degrees. That makes our angle 90. But sometimes it's just easier to know that if you're looking at an inscribed angle that shares endpoints with a semicircle, you'll have a 90-degree inscribed angle. I may be going a little fast, and I'm sorry about that, but feel free to pause at any time and review this stuff because this is very important stuff. So let's talk about intersecting chords. Intersecting chords are interesting to me in that I get to bring back a vocabulary word that you guys may not have heard in a while, and that is vertical angles. So I don't feel like we need to define what intersecting arcs are, or chords, intersecting chords. We know that chords are lines that span across the circle, right? And I believe we all know what intersecting means. It means they meet at some point, they share that point. So intersecting chords bring back that vocabulary word of vertical angles. Let's say intersecting chords form a pair of vertical angles. And what do we remember about vertical angles? I'll give you guys a second, and you should be able to pick it up from this image over here. But we should remember that vertical angles are always congruent, meaning they share the same measure. So let's look here. We have these two chords. We have chord DB, and we have chord CA. And they create some angles there. We won't necessarily write out the angle names, but we can see that each of these angles equal 117 degrees. So angle C, we'll call this center point O. So angle COD is 117 degrees, and angle AOB is 117 degrees. So where's the connection to be made here? Well, so you see we have 144 over here and 90 degrees over here. So there's got to be some relationship there, right? Right, there is. So here is another important fact. I like to think that all the facts I give you guys are important, but I'm going to start emphasizing the ones that I want you to know. I may quiz you guys on these sometime soon. Just a little pop quiz. Let me know what you guys are learning and not learning. Remember these. Okay, important fact. The measure of each vertical angle created by intersecting chords is equal to half the sum of the intercepted arcs. Whoa. Let's take a second to take this all in. So we say that the measure of each vertical angle, so each one individually, is equal to half of the sum of the intercepted arcs. What does that mean? What does sum mean? Sum means is the end result of addition, right? So the sum of the intercepted arcs. Well, we have our intercepted arcs circled, so we have 144 and 90 degrees. So let's go ahead and add those up because we know we need the sum of them somehow. So throw a little addition sign there, and that would equal, no, not 134, 234 degrees. So the measure of vertical angles created by the intersecting chord is half the sum of the intercepted arcs. So we have the sum, and we need half of that, right? It says something about half of the sum of the intersected arcs. So if we do 234 divided by 2, we get You may have guessed it. I'm sure you did. 117 degrees. So it's important to know here that it's not the sum of the intercepted arcs divided by 2 is the total measure of those vertical angles, but it's of each. So in any case where you have two chords intersecting, you can get these chord measures, or these arc measures, excuse me, and you can add them together and then divide by 2 to get yourself the measure of either of these vertical angles. We'll do an example. One example, and then I'll let you guys go. All right. So we have some intersecting chords here, and we want to figure out, in this case, what arc AC is. So let's write down the information we have. We know that angle CBA equals 47 degrees. And we know that angle DBE equals 47 degrees. And we know that arc, we'll write it up here by the other arc, EC equals 29 degrees. So let's think about that formula we use. We said that if you add up the two intercepted arcs and divide by 2, you'll get the measure of the vertical angles, which in this case is 47. So we can say that whatever AC is plus our 29 degrees of ED divided by 2 is going to equal 47 degrees. Here's the trick, guys. This one is in your notes. This is in your guided note sheet. So I'm going to do one more step for you, and then I'll let you guys do the rest to prove to me that you guys are actually watching how to do this and whatnot. So we're set up with this where we need this question mark. Well, you know what? We'll call it X to make it a little bit more algebraic for you. So we need to solve for X. I know you guys love solving for X. So the first thing to do here is multiply both sides by 2. So you would be left with X plus 29 degrees equals 47 times 2, which is the same as 40 times 2 is 80, and 7 times 2, which is 14. So you're left with 94 degrees. So what's this X equal? X equals what? And I'll let you guys solve that in your notes. I hope this all came pretty easily to you. I know it's a lot to take in as far as, I mean, look at how much we wrote today. This is a lot. And I hope that I've emphasized the importance and where the importance lies with certain facts and whatnot. The truth is that everything on this you need to know for the test. And I hope you all can do that and not struggle with it too much. But I appreciate you guys watching this far. And make sure you get that solved for X in your notes. If you need anything at all, feel free to reach out to me or Mr. Rose. And we'll get back with you as soon as possible. Remember, on the days you guys are virtual, we do have those Google Meets open on your class times. So jump in there, ask us a question. We're just sitting there waiting. So if you have even a simple question about one little thing, like, is this answer right? We're there for that. So do not be afraid to utilize the resources available to you. Thank you guys for watching this, and I hope you are prepared for the next video, because the next one is even more fun.